So magnetic and capacitive coupling for EtherCAT or Ethernet. Copley recommends magnetic coupling, but I find myself supporting people that are trying to do capacitive coupling. Capacitive coupling is okay as long as we follow some rules, and I'll go over that. This is an example of a 4-axis AEVs mounted to a mounting board, or they call it a backplane in the EtherCAT speak or Ethernet speak. And you can see I've got node 1, coming in. You hit node 1 and then go to node 2 and then 3 and then 4. And these are mounted on the back side of the board, which attaches to a heat plate to get the heat out. This is just a fixture for probing. And then if we turn it around and take a look at the front side, you can see we got some M12s for EtherCAT in and then EtherCAT out. And after a long cable, you'll definitely want to use the magnetics. This is using a halo. And then you go around the board through in and out the drives, and then you go back out through your out port and magnetics again. So anytime you have a length of transmission, you definitely want the magnetics. But you can see even in this board, we've bypassed the magnetics here. Copley uses magnetics and recommends magnetics. It's just better. But you don't have to use magnetics. You can use capacitive coupling. That's what everybody asks about. It even works if you short them out, okay? So I'm not saying that we should short out the connections. We should use capacitors because that's what everybody says we should use. But as a matter of fact, it actually works with just a direct connection. Why? Well, because the traces are managed properly. Just FYI, this will be the Nano, and it looks like we could probably mount about 8 of these to one board. So instead of just a 4-axis robot controller, it could be an 8-axis robot controller, or it could be a much smaller 4-axis robot controller. So let's take a peek at the calculation for the capacitance, and assuming you've got 100 ohms of transmission characteristic impedance of your twisted pair, at least it has an outer braid, but some people use inner foil shields, but it could be unshielded twisted pair, but I think the shielded twisted pair is the recommendation because we have the shields have a path to Earth at the master and passing through the drives, and I believe we even connect the shield to Earth at the drive. I have to double check that, but you can see based on your frequencies and your characteristic impedance, you can come up with a calculation. It's all based on IEEE 802.3. 33.4.7, and this is a great note for doing similar stuff with analog devices. Highly recommend analog devices. And they reference the IEEE standards. Here we are using magnetics with analog devices, and here we are using capacitive coupling for the transmit and receive pairs coming in and going out. This would be coming in and going out of a board after cables, and this would be on the board or backplane with capacitive coupling. Again, I'm still going to recommend magnetic coupling so we don't have any problems, but if you want to save a little bit of space and a little bit of money and you're the design engineer, you don't need me to design your product, so do capacitive coupling, just follow the rules, right? Let's take a look at application note here from Copley. And this was developed by the design engineers, and I added some pictures. So just for starters, you can see a lot of these cables are already available. The Cat5 shielded with unshielded twisted pairs, so S UTP. 100 base T is the EtherCAT. Pretty typical unless you're talking the 1 gigabit, but there's not a lot of hardware ready for that yet. But Ethernet IP, here's an example of PROFI NET doing the M12 connectors. They love those M12s, and we need some cable. Only need 4 wires technically. 8 wires fine. You can have redundancy that way. If you have 4 wires, you can't have the redundancy, but a lot of controllers or masters don't manage the redundancy anyway, so what's the point of buying the cable? This 4-wire cable is pretty good, maybe save some money. On the other hand, it's not very popular, so maybe you spend more. You can see the pinouts and the colors for the different transmit pairs. And here's a note from the PROFI NET team for how to get from your undesired RJ45, which is just fine, most popular. And I like the M12 too, don't get me wrong, but a little more expense for no real gain as far as I can see. A little bit about the magnetic coupling. And so in the data sheets and the development reference designs for the Nano EtherCAT standard drive, you can see the pinout for the RJ45 connector coming in and going out. So you got in and out, should be labeled. And here's the magnetics. They can be in the connector, right? Or we can use the Halo chip separate. So there's a couple of reference designs. The Easy Kit uses the chip because it was just easier to use the chip than it was to get a great big connector. We have little tiny connectors for the Easy board. So if we use the Halo, there's some larger Halos and some smaller Halos that always coming out with new smaller stuff. It's pretty cool. Capacitive coupling again. IEEE 802 standard, 802.3 is a good reference. And here's the example of coming in to the magnetics. And then first node, there's a port 1 and a port 2. And I'll talk a little bit more about that because we need to program the drives, whether they're magnetic or whether they're capacitively coupled to each other. So there's a port 1 with the magnetic and a port 2 with cap. This node has port 1 and port 2 with caps on both sides. And then the last node, whatever that is, N or N plus 1, the port coming in is capacitive, but the port going out goes through inductive. And then you go off to your next controller with the cable, and you have magnetics again, and that's just a good practice. So we talk about the backplane or the mounting board. Again, if you're going to lay out some traces, right, in your board, you can see that there's a black backplane rule, but they're together for transmission of 100 ohm characteristic impedance. They're slightly separated. We don't run stuff across it. We don't cross over. And so we try to get a good trace from the Halo chip off to the drive without introducing crosstalk and interference. So transmit pairs should be routed as differential pairs. You see this is together as a pair. Differential pairs should be routed slightly away from each other if possible. So, hey, there's some distance here, and it got a little closer, but it's not too close, and then it got further away. So that's good practice. Individual pairs should be routed together as possible with impedance control. So here's a pair with 100 ohm impedance control. Each differential pair trace should be matched in length, right? That's important. You can't have one longer than the other, otherwise it's not a matched pair. So there's some tricks for that for board layouts, and this doesn't really show any tricks here. It's just keep them similar distance, and it's very close. I think the inner loop might be a little shorter than the outer one, but I don't think it's that far off. No signals should cross unless properly separated by ground plane layer to avoid crosstalk. The use of vias, like it's not a good idea to go up and down through the board, so just keep it all on the same plane. You got to disable the Auto-MDIX between ports with no magnetics. So that's what I was talking about, like port 1 and port 2 in and out of the drive. If you're on the side with the capacitive, you need to disable that port. And here's a parameter 0x121, which talks about turning those bits on and off. So for node 1, bit 5 disables Auto-MDIX on port 2. That's going out. So coming in is magnetic, going out is capacitive. On the next node, we got capacitive on both sides, so we disable on both sides, port 1 and port 2. And on the last node, before the magnetics, we disable on, the coming in, but the going out has magnetics, so port 1, not port 2. And so we set the bits in the drive parameter for the network configuration 0x121. This is the latest rev of the document, and I think that's it. We could talk more about the signals for the EtherCAT. I have a little time. Let me dig that up. Hold on. Hot connect group. Okay, so we're going to take a look at the EtherCAT here. Hot connect group. That's not a good idea to do hot swapping of anything. So I'm going to say don't do this. And also, most masters only have one cable coming out, and they don't have the redundant coming back. So this is a little odd to me, but let's talk about why somebody might want to do this. But don't hot connect, okay? Because we're turning off the MDIX. So I don't know if that works. It probably doesn't. But typically you have an EtherCAT master with one Ethernet port. This is a good network interface card. And you got your transmit and receive. It's 4 wires coming in, going to the next. And so at the last node, it comes back around. So a pair goes in and a pair comes back. Everybody's happy. You see the smiley faces. That's good. Oh, I disconnected things, and these other guys are not so happy. Well, of course, don't unplug the cable. Okay, if you have to unplug the cable, I don't know, maybe there's some sort of safety requirement. I need to unplug the cables. These nodes will come to a stop, right? That's what happens when you unplug cables. You don't have a master. The slave goes into a command input fault. We get a trajectory abort. We stop, and we could disable or hold position, depending on how we configure the slave. But we're not continuing to move when we become unplugged. There's node guarding. But the idea is redundancy. So you have another network interface card with another port, which if this one gets cut, these two guys still have connection to a master, and they can be happy, and you just keep moving. Or maybe you don't. Maybe you saw an event where a cable comes unplugged and you stop anyway. So this just means you have more work to do in your master software. I don't think everybody manages that yet. But, that's why there's an 8-wire system here for the redundancy, but 4 wires should be sufficient. Yeah. This is the EtherCAT field bus, and 100 drives and 100 microseconds. The messages don't receive, calculated, and retransmit. It's where's the picture of the train? Yeah, the train's coming through the station. It never stops. You change your bits as it comes in and goes out. So that makes it fast. It's a giant Ethernet message, standard Ethernet message. Yeah, they're better than everybody else, of course, blah, blah, blah. It's supposed to be easier. I don't know. It's a bigger message, takes longer than a CAN message, but hey, if you say you're better, you must be better, right? So I take issue with that. Oh, everybody knows how to do Ethernet. Well, of course, because they learned it. And CAN is very similar, and it's still in cars, and it goes faster now. Distributed clocks is great, but you have to make sure you know how to use them and configure them properly. Most masters can do it now. In the beginning, people had problems with their distributed clocks, but the advantage of the EtherCAT is plus or minus 40 nanoseconds, or plus minus 20 nanoseconds, so 40 nanoseconds of jitter. That's pretty cool. So timing can be pretty accurate in Ether.